I am Dr. A. Kalpana, Associate Professor of Chemistry, PG and Research Department of Chemistry, Sri Sharda College for Women, Salem 16. Now let us see about Diels-Alder reaction. What is Diels-Alder reaction? It is a cycloaddition reaction and it belongs to 4+2 cycloaddition reaction. It is thermally allowed and photochemically forbidden. Now let us go in deep. Diels-Alder reaction is a reaction between a conjugated diene and an alkene or alkyne, which is also called as dienophil. Therefore, a Diels-Alder reaction is nothing but a reaction between a diene and a dienophil. A dienophil may be alkene or alkyne, substituted alkene or substituted alkynes, and both these substrates adds together and forms a cyclic transition state, mostly 6-member, and forms the product. And this is the mechanism. This bond will go inside and this bond will go in between this carbon and this carbon, and this bond will come between this carbon and this carbon. Therefore, we will get a cyclic transition, 6-member cyclic transition state, and then the product formation. All the Diels-Alder reactions are syn addition reactions, and this is an example. If the dienophil is cis, we will get cis adduct, and if the dienophil is trans, we will get trans adduct. The product of Diels-Alder reaction is called as adduct. And see here, hydrogen cis, COO-CH3, COO-CH3 cis to each other. This is a cis dienophil and we will get cis product. Here the reaction will be like this. The bond goes here. This bond goes between these two carbon, that is this carbon and this carbon. And this bond will come here, that is between this carbon and this carbon. Therefore, we will get a cyclic product. Here see, this is a new bond formed here. And this is a cis product. Syn addition will take place, and here also syn addition, the bond goes inside, this will go here between this carbon and this carbon, this bond will come here, that is between this carbon and this carbon. So we will get a new pi bond here. See, this is a new pi bond formed. This is a cyclic adduct, that is, since the dienophil is trans, syn addition will occur and the trans adduct will be formed here. That is the loss of 3 pi bonds, and see here this pi bond will go, this pi bond will come here and form a new pi bond here. Okay, this is another example. This bond will go here. That is, cyclic shift of electrons will take place. Cyclic shift of electrons. This bond will come between this carbon and this carbon. And this pi bond will come between this carbon and this carbon. This pi bond will goes here. This is a newly formed pi bond. We can understand. And there is a formation of 6-member ring here. So this is the Diels-Alder product. Diels-Alder reactions are stereospecific in nature. Now let us see some examples for stereospecificity of Diels-Alder reaction. Now let us take one dienophil. See, this is one dienophil we are taking, and this is where we are taking different types of dienes, and we are checking the stereospecificity here. We are going to check the stereospecificity. See, this is the dienophil. First, let us take this diene, cis diene. And the substituents are outside here. Let us consider these two R substituents are outside. See, what is the rule here? Outside substituents of the diene are always below the plane of the new 6-membered ring of the adduct. See here, this R and R substituents are outside, and in the product they are below the planes. Below the plane. See, this R and this R are below the plane. We are taking cis diene. And now if we take trans diene, that is, the H and H is outside now, and according to our condition, the H and H in the product will go below the plane. So this and H is below the plane of the new 6-membered ring of the adduct. And coming to this diene, cis trans diene. So which is outside now? R and H is outside. In the product, R is also below the plane and H is also below the plane. So from this example 1, what is the inference we are getting means outside substituents of the diene are always below the plane of the new 6-membered ring of the adduct. Coming to second type, inside substituent will be above the plane of the 6-membered ring of the adduct. See here in this is diene and this is dienophil. What will happen? This ring will go in. This pi bond will go in and this pi bond will come out between this carbon and this carbon. This pi bond will come down between this carbon and this carbon. Therefore, adduct will be formed. It is a general one. And the phenyl substituents which is inside the diene, which is considered as inside substituent, will now be above the plane of the product, above the plane in the product. See here, in this bond, phenyl ring, and this in this bond, the phenyl ring will be there. This is the conclusion we are getting. And coming to this example, this OAC is considered as inside substituent and this OME is considered as outside substituent. What is our consideration? Inside substituent will be above the plane and outside substituent will come below the plane in the product formed. So this bond will go in, this bond will go up and this bond will go down, and there is a formation of usual 6-membered ring. The OAC, which is considered as inside substituent, will be present above the plane in the product, and OME, which is considered as outside substituent, will be present as below the present as a substituent below the plane in the product, that is in the adduct. So from these examples, what we have considered is outside substituents of the diene are always below the plane of the new 6-membered ring of the adduct, and the inside substituent will be above the plane of 6-membered ring of the adduct. And coming to second series example, cis product will be formed from trans diene and trans product will be formed from cis diene. See here, we are taking trans diene. How we are considering this as a trans? This hydrogen and this hydrogen are trans to each other. See, this hydrogen is above this carbon and this hydrogen is below. So these two hydrogens are trans to each other. Therefore, this is considered as trans diene. Whereas here, see, the hydrogen are on similar sides. Here the hydrogens are on opposite sides. Here the hydrogens are on similar sides. Therefore, it is a cis diene. Trans diene will form cis product and cis diene will form trans product. That is the rule here. So now Diels-Alder reaction takes place. The pi bond will go in. This pi bond will go up. That is between this carbon and this carbon. And this pi bond will go down between this carbon and this carbon. Therefore, ring will be formed. 6-membered ring is formed here. Now see what happens. Seeing the substituent, see here, cis product is formed. Both the hydrogens are on same side. Here see, both the hydrogens are on opposite sides. One is in this bond, one is in the other type of bond. See here, both the hydrogens are on same side, similar bonds. See here. Same side, that is cis product. Opposite side, that is trans product. So what is the conclusion we are getting from this example? Cis product will be formed from trans diene and trans product will be formed from cis diene. So two types of conclusion we are having. Outside substituents of the diene are always below the plane of the newly formed product, and inside substituents of the diene will be above the plane in the newly formed product. And cis product will be formed from trans diene and trans product will be formed from cis diene. This particular example will indicate this conclusion. And coming to the next one, Diels-Alder reaction between these two, diene and dienophil. We will get a cyclic product. Here see, we get endo product and exo product. Bicyclic product we are getting here. Here this exo product is more stable. Why? Means this substituent is pointing away from the congested part of the bicyclic ring. Therefore, the exo product will be more stable. Even though there is a formation of endo and exo will be the more stable one. Here also there is a formation of two types of products, exo and endo. Endo will be more stable because the substituent will point out away from the congested two rings are there here. See here. This is one ring and this is one ring bicyclic. Here also another ring. This ring will point away from these two rings. Therefore, from these examples, what the conclusion we are taking means all the Diels-Alder reactions are stereospecific in nature. And coming to the important factors in Diels-Alder reaction, what is the criteria for a good diene? What is the criteria for a compound to act as a good diene? The compound should be electron rich. The compound that is going to act as a diene should be electron rich. Therefore, it will have high reactivity. An electron poor diene giving Diels-Alder reaction is rare. And presence of electron donating groups such as alkyl, phenyl and alkoxy group may further enhance the reactivity. So, the main condition is the group should be electron rich. Therefore, it can possess high reactivity and it should have electron donating substituents so that it will enhance the reactivity of the Diels-Alder reaction. And it can be open chain or it can be a cyclic. The diene may be a open chain diene or it may be a cyclic diene. No issues. And the diene should possess cis conformation. The diene should possess cis conformation to give a Diels-Alder reaction. If it is having an S-trans conformation means it should have the ability to rotate and forms a cis conformation. It should undergo rotation to form cis conformation. Then only it can undergo Diels-Alder reaction. Why? What is the reason? Because S-trans diene is not having such conformation to undergo addition. See here, S-cis diene means there is no issues. It will undergo Diels-Alder reaction. S-trans conformation that cannot adopt S-cis conformation will not give Diels-Alder reaction at all. If it undergoes reaction, if it is having capability to undergo rotation and form cis-trans conformation means it will undergo Diels-Alder reaction. The S-trans conformation that cannot adopt S-cis conformation cannot undergo Diels-Alder reaction. And if the diene is in S-trans conformation, what is the reason? It is not capability to undergo, it is not having capability to undergo Diels-Alder reaction because the dienophile could not reach the both ends. See here, if it is having S-trans means this is one end of the diene, this is another end of the diene. How the dienophile can approach this? It cannot reach the both ends at the same time. If it is having S-cis means the dienophile will reach directly and forms the Diels-Alder adduct. But if the diene is in S-trans conformation, the dienophile cannot reach both ends of the diene at the same time. Because the two end p orbital is more important for the overlap, isn't it? If the two p orbital, they will be too far apart to overlap with the dienophile. Therefore, S-trans conformation cannot undergo Diels-Alder, but if it is having capability to rotate and forms S-trans conformation means then it will undergo Diels-Alder reaction. See here, it is having a trans conformation. See, the diene is having trans conformation. In this also, the diene is having trans conformation. Therefore, it does not give Diels-Alder reaction. Dienes, and the another condition is dienes with functional group that hinders S-cis conformation reacts slower than butadiene, which is considered as a common diene, general or standard diene. Dienes with functional group that hinders S-trans conformation reacts faster than the butadiene. This is another important point. See here once again, functional group that hinders S-cis conformation reacts slower than butadiene, whereas the functional group that hinders S-trans conformation reacts faster than the butadiene, and these are some examples for you. Here, these two substituents will hinder S-cis conformation. Therefore, it will undergo Diels-Alder much slower than butadiene, whereas this substrate will undergo the rate similar to butadiene for a Diels-Alder reaction. Whereas this one, these two substituents, see here, will not hinder cis-trans conformation. S-cis conformation. Therefore, it will undergo faster than butadiene. And this substrate will undergo much faster than butadiene. Coming to dienophile, what are the criteria for a compound to act as a good dienophile? Most common dienophils are electron-poor alkenes and alkynes. Here, the dienophil must have electron withdrawing groups, whereas diene should have electron donating groups to enhance the reactivity. Dienophil must have electron withdrawing groups to enhance the reactivity. Simple alkenes or alkynes cannot act as a good dienophil, such as ethylene or acetylene are not good dienophils at all. If it has electron, one or more electron withdrawing group, then the reactivity enhances or the reactivity increases. And dienophils may be conjugate, it may be conjugate with carbonyl groups or nitro compounds, nitriles, sulfones, aryl alkenes, aryl alkynes, vinyl ethers, vinyl esters, haloalkenes and dienes. So the main condition for a dienes or the compound should be electron rich and should have high reactivity, and it should have electron donating group to enhance the reactivity. It may be open chain or cyclic. It should possess S-cis conformation. S-trans conformation, diene with S-trans conformation cannot undergo Diels-Alder. If at all it has capacity to rotate and forms S-cis conformation. The S-trans conformation that cannot adopt S-cis conformation does not give Diels-Alder at all, because the n-p orbital of the diene will be too far apart to overlap with p orbital of the dienophil, and the functional groups that hinder S-cis conformation reacts slower than butadiene, whereas that hinder S-trans conformation reacts faster than the butadiene. These are some of the examples. And coming to dienophil, simple alkenes or alkynes cannot act as a good dienophil, but if it has one or more electron withdrawing groups, then the reactivity increases. And the dienophils conjugated with some electron withdrawing groups may act as a good dienophils. And coming to stereochemistry, Diels-Alder reactions or syn additions, already we have seen some examples. And the Diels-Alder reactions are stereospecific, for that also we have seen some examples. Coming to orientation effect, it is a more important factor in Diels-Alder reaction. Let us see some cases regarding orientation effect. Case 1, electron donating group in the middle carbon of the diene. Electron donating group in the middle carbon of the diene. See here, now I am placing an electron donating group in the middle carbon of the diene. D represents electron donating group and W represents electron withdrawing group. Already we have seen that diene should have electron donating group and dienophil should have electron withdrawing group. That is the proper one, standard one. Now we are giving Diels-Alder reaction here. See here, 1,4 product is formed. 1,3 product formation is also a possibility, but it is not formed here. So if electron donating group is in the middle carbon of the diene, then 1,4 product is the dominating product. 1,4 product is formed. There is no other no other product formations. See, this is a mechanism given here. See here, OCH is an electron donating group, and we are aldehyde group. CH was an electron withdrawing group in dienophil, and the mechanism goes this way, and there is a formation of 1,4 product. Even though there is a possibility for 1,3 product, it is not formed here. That is the case 1. And case 2, electron donating group in the terminal carbon of the diene. We are placing electron donating group in the terminal carbon, means 1,2 product is formed. If it is placed in the middle carbon, means 1,4 product is formed. If it is placed in the terminal carbon, means 1,2 product is formed. Here we are placing an electron withdrawing group in dienophil and electron donating group in diene. That too, the electron donating group is in terminal carbon. So what is the product formed here? 1,2. Even though there is a possibility for 1,3, it is not formed. 1,2 product formed. 1,2 product is formed here. So we are placing this OCH in the terminal carbon. There is a form. See here, the bonding electron will go here, and this bonding electron will go here, and this bond will go to form a bond between this carbon and this carbon. So that this is formed, and the product formed is 1,2 product. So once again I am saying that if the electron donating group is in the middle carbon, 1,4 product is formed. If the electron donating group is a terminal carbon in diene, then 1,2 product is formed. This is the orientation effect. So what are all the effects that affect the reactivity of the Diels-Alder reaction or the Rate of the Diels-Alder reaction means number 1, diene, nature of diene. Number 2, nature of dienophil. Number 3, stereochemistry. Number 4, orientation effect. And all the Diels-Alder reactions are considered as stereospecific. Thank you.